In this video, I want to teach you how to calculate the pH of weak acids as well as weak bases. So, in previous videos and in class, we've talked about the difference between strong and weak. Strong means that it dissociates 100%. Weak means that the dissociation is very, very small, around 1 to 3%. So because when we have strong acids, because they dissociate 100%, whatever concentration that the acid is, or the base, as long as it's strong, is actually equal to the concentration of the hydronium ion or of the hydroxide ion. So we can just directly plug it into the pH formulas to solve for the pH of those. The problem with weak acids and weak bases, however, is that we don't know the percentage that it dissociates. We know that it's only dissociating a small amount. And basically, how much it dissociates is based upon its Ka value. We also talked previously in a video that as your Ka increases, the strength of the acid increases. If the strength of the acid decreases, that means it's dissociating more as a higher percent dissociation than others. So when we are trying to figure out the pH of weak acids or weak bases, our goal is to figure out how much of the hydronium ion or how much of the hydroxide ion, if I'm working with bases, that I have. If I know that amount, then I can plug it into my pH formula or my pH formula if I'm working with bases. Now the question is, how do I figure out that amount? Well, what I'm going to do is set up a Rice chart. So when I set up a Rice chart, I first have my reaction. We did this with equilibrium, right? We're working with Ka values, so we're working with equilibrium Rice charts. So when I'm doing that, I'm going to write my reaction of dissociation. Now, you could write it like this, or you can write it like, this is probably what you're more familiar with, HC2, H3O2, plus water, because when it's dissociating, it's going to be in water. And we have an acid plus a base here. Now our acid is donating the proton, so it's going to be H3O plus C2H3O2 minus. And we have our conjugate acid and our conjugate base. So this is all we're doing is writing that reaction of this acid-base reaction. Now, water is a liquid. So remember, back from equilibrium, if we have liquids or if we have solids, we do not include them in equilibrium. And we're dealing with K here, so yes, we do not include water. What I'm going to do is I'm going to plug in that concentration of the acid that I'm starting with. So 1 times 10 to the negative fourth. Initially, this is initial, right? I have 0 hydronium, 0 of the acetate ion. Now I'm going to fill out the rest of my Rice chart. I have minus X, I have plus X, and I have plus X. Now, what is the point of setting up this Rice chart? What are we trying to do? Our whole objective here is to figure out the concentration of H3O plus at equilibrium. If I know the concentration of H3O plus at equilibrium, then I can plug it into my pH formula. So, what I'm going to do is finish my expression. So this ends up being 1 times 10 to the negative fourth minus X. This is X, and this is X as well. So my objective is to find some way to solve for X, because X is the hydronium ion concentration. And if I know the hydronium ion concentration, I can calculate the pH from there. So what am I given to help me solve for X? If you remember from the equilibrium values, we were given like a percentage, which we're not given here, like a percentage changing. We were given one of these equilibrium values, which were not given here, or we were given a K value. And if you look up here in this example problem, we are given a Ka value. So what we're going to do is we're going to use this Ka value, set up our equilibrium expression. You should know what I'm talking about when I'm saying this. And then we can solve for x. So my equilibrium expression here is going to be, I'll write it up at the top here, Ka is equal to products raised to the power over reactants raised to the power, and the powers are the coefficients. Remember, pure liquids, pure solids are not included. So what this is going to look like is H3O plus concentration. Remember, I have to put the brackets because that denotes concentration. C2H3O2 minus concentration over C2H3O2 concentration. So this is my equilibrium expression. Now that I have my expression written, I can plug in values. So my Ka value is 1.8 times 10 to the negative fifth. My H3O plus is x, and so is this. So you see how we can simplify that as x squared. X times x is equal to x squared. These are equal to one another. Over 1 times 10 to the negative 4 minus x. Now, we have a little bit of a situation here. If I take this and I solve for x, you see how this number here is going to have to distribute here, and it's also going to distribute here. So I'll get whatever this number is times whatever this number x is equal to x squared. That's going to pose a problem in my math. Now, we could definitely do it, but it's just going to make my math a little bit more complicated. We're going to have to end up doing the quadratic formula in order to solve for x. Well, in chemistry, we have something called a 5% rule. And basically, what this 5% rule means is that you can figure out of whether or not this x, let me use a different utensil so you can see which one I'm talking about, this x right here, whether or not it's significant. So what I mean by that, if this x is a very, very, very small number, then if I subtract a very, very, very small number from this number, it's not going to change this number very much, if at all. So what I could do is neglect this x. Only this x is the one that I can neglect. All right? So you do something called a 5% rule to see if this number is basically negligible, if it's insignificant, if it's not going to change this number that I have here. If it fits the 5% rule, then I can neglect the x. If it doesn't, then sadly I would have to do the quadratic formula. Now here's the good news. AP is not testing you on your math skills, so you will not have to do the quadratic formula. So you always can assume that this is in the 5% rule and you can neglect your x value. But here's what you have to show in order to get the credit. You have to plug it in to your expression. You have to show this little x. You can mark it out and say neglect x, and then you can pretend like it's never there. So this now is going to make our math a lot simpler. We have 1.8 times 10 to the negative fifth times 1 times 10 to the negative fourth. That's something very easy, is equal to x squared. So whatever this number times this number is equal to x squared. So I would take the square root, and the square root of that number will end up being x. So I'm going to write it up here in this little margin. The x that I found for this particular example is equal to 4.2 times 10 to the negative fifth. And I made that simple again because I was able to neglect this x because of the 5% rule. Now, we found x. That's all fine and dandy. This isn't math. We need to know what x means, okay? Math, you just get a number. But for chemistry, we have to understand what that number means. X, if you remember, is the amount of the hydronium ion at equilibrium. So it is equal to the concentration of H3O plus. Now, this isn't answering our question, it's just helping us answer our question. The question is, what is the pH? Well, if I know this concentration, I can figure out the pH because pH is equal to negative log of H3O plus concentration. So what I'm going to do now is I'm going to plug this number into here, take the negative log of that, and that will give me my answer for my pH, which ends up being 4.37. So that is our final answer for the pH of this weak acid, which is acetic acid. So let's do a recap. What do I do if I'm trying to figure out the pH of a weak acid? Because it does not dissociate 100%, and we don't know exactly the percentage that it does dissociate, we have to set up a Rice chart to solve for our hydronium ion concentration. So we're setting up our Rice chart, we're setting up our Ka expression, and we're solving for the hydronium ion. Once we figure out the concentration of the hydronium ion, we then can plug that into my pH formula. So here's my next question. This is how we take the pH of a weak acid. How is the pH of a weak base? How might that be different? Well, here's what we do. If I have a weak base, I am not dealing with hydronium ions, right? Weak bases have more hydroxide ions. So my base will have OH minuses here instead of H3O pluses. Well, because I'm also dealing with a base, I'm also going to have OH minuses, but I'm going to have to use a Kb value as well. If I use a Kb value and I solve for X, that X is going to be my OH concentration. And if my X is my OH concentration, I can't find pH. Instead, I'm going to have to find pOH first, and then I can subtract from 14 to solve for my pH. So let me do an example with you to make sure that you understand this. Let's go to page 15, and in our packet, I'm going to pause you for a second so I can get there. All right, so here we are on page 15 of the notes, and exercise 15 is what we're looking at. So we want to calculate the pH of a 15 molar solution of NH3. So NH3 is our base there. First thing, what are we going to do? Well, first of all, we recognize that this is a weak base, so we know we're going to have to set up the Rice chart because it's not 100% dissociation. We have to figure out the amount of the OH that will actually get there. So what I do is I take NH3 plus H2O, I'm writing my reaction here, and when those combine, this is the base, so that must make hydrogen, the water, the acid. So the hydrogen is going to be donated here, so it's going to make NH4 plus, hydrogen ion I should say, plus what's left over of water, which is OH minus. So you see how you don't have any H3O pluses here. So that lets us know that 1, I'm going to have to solve for my OH concentrations, and 2, I have to use a Kb value to get that. Water is not included, so I'm going to put in my initial concentration for NH3, my initial concentration there and there. So all I'm doing is setting up my Rice chart. You guys should be good at this because you have done equilibrium before. So we have 15 minus X, we have X, and we have X. So now, what is our next step? Well, now that we have our Rice chart filled out, we're going to write our KB expression. KB, because we're dealing with a base. So that KB value is going to be NH4 plus times OH minus over NH3. Water is not included because it's a liquid and solids and liquids are not included. Now that we know our KB expression, I'm going to plug in my values. So we have, let me use a different marker here. KB is 1.8 times 10 to the negative fifth. We get x and x, so that simplifies to x squared. And NH3 is 15 minus x. So, because AP always applies to the 5% rule, we can neglect this x there to make our math simpler. We don't have to do the quadratic formula. So now I'm going to cross multiply 1.8 times 10 to the negative fifth times 15 is equal to x squared, and then I would take the square root. So you end up getting x is equal to 0.0164 molar. Now, again, what does x mean? All these numbers in chemistry have a meaning. The x is the OH concentration. So that's the OH minus concentration. So now what I can do is I can find or start to solve for a pH. Now I can't just directly plug this into my pH formula because I need to know the hydronium ion concentration to find my pH. So what I'm going to have to do first is find a POH, because I have OHs here, which would be negative log of OH minus. And when I take the negative log of this number, I end up getting 1.78. Now, the answer wants us to be in pH instead of POH. So, how do I get to pH from POH? All I do is I take 14 minus this number, because the pH scale is 1 through 14, so pH plus POH should equal 14. So 14 minus 1.78 will give me my value, which ends up being 12.22. And that is the pH of our weak base if it's 15 molar NH3. So that's how we figure out the pH of weak bases. We just have to do an extra step because it's OHs we're dealing with, so we have to find a POH first. Now I have one question. What if AP wants to throw you a curveball, and instead of giving you a KB value, they gave you a Ka value instead? There is a way that I can transfer from Ka to Kb. So I'm going to go ahead and show you this, and I'll show you it again whenever we do buffers. The value that we found in our pH things, 1 times 10 to the negative 14th. Remember how we said that the hydronium ion concentration times the hydroxide concentration, those will always equal to be 1 times 10 to the negative 14th. Well, because Ka is relative to strength, and strength is related to how much of these hydroxides or how much of the hydroniums we actually get, this number is also equal to your Ka times your Kb value. So, if I was given a Ka value, but I needed a Kb value because I was dealing with a base, then all I would have to do is take 1 times 10 to the negative 14th divided by that Ka value, and that's equal to Kb. So this is a good little side note, something to put in your notes that is important, especially when we get into buffers. So what I showed you is how to take the pH of a weak acid and the pH of a weak base. There's one more thing that I want to leave you with. So I'm going to scroll back up to, I think it's page 14, calculating percent dissociation. Let's talk about what that means. So on page 14, we see calculating percent dissociation. Remember how I've been talking about like strong acids, they dissociate 100%, but weak acids, weak bases, they don't dissociate 100%. It's a very low percentage. We can actually calculate that percent dissociation. So I want to leave you with the way to calculate that percent dissociation. So here's your equation. Percent dissociation. So you don't have to memorize this equation. I want you to make sense of it. Dissociation means how much of the H+, the proton, is being dissociated away or broken apart, split apart from the acid. So it's like a part over whole. It's a percentage, a part over whole type of equation, like when we do mass percent and stuff like that. Our part is going to be the concentration of the hydronium ion, H3O+. The whole is going to be what it dissociated from. So I'm just going to put HA here for the generic form of an acid. It's an H with something else, an H with something else, okay? So I'm going to take my part over whole, the part being the H3O+ that's dissociated, the whole being the acid that I started with, and I'm going to multiply by 100 to get my percentage. So if I want to figure out the percent dissociation, and then I've given a Ka value, I need to know how much of the H3O+ that I have. I already know the whole acid concentration because it's given to me right here. So how can I figure out this amount of H3O+? Well, all I'm going to do is set up that rice chart and solve for X using my Ka value just like I did for pH. But now I don't have to plug it into the pH formula. I'm just going to plug it in right there. Okay? So let me go through an example with this here. I'm going to write my reaction. So HC2, H3O2 plus water. When it dissociates, it's going to, or when we have our reaction take place, acid donates the proton, base receives that proton. So we have H3O plus C2, H3O2 minus. Water isn't included here. We have 1 molar starting here, 0, 0, minus X, plus X, plus X. We have 1 minus X, X, and X. So now we write our expression. So Ka is equal to H3O+ times C2H3O2 minus over HC2H3O2. And now we get to plug in our values. So we get 1.8 times 10 to the negative fifth. We get x squared, and we get 1 minus x. Also for this, yes, we get to neglect x. So I'm going to take this number times 1, which is itself, take the square root, and you end up getting, let's see, which one am I working with? 0.0042 is equal to x. So x is equal to 0.0042 molar. Again, what does that number mean? It's the amount of the hydronium ion concentration that I have. So now that I know the amount of the hydronium ion concentration, I can plug that number in here. My HA is 1. So I take 0.0042 divided by 1 times 100, and you get your percent dissociation, 0.42%. So this is how you find your percent dissociation for weak acids. I could even do this for weak bases as well. They could also ask you to figure out a Ka value. So if I knew my percent dissociation, I could work backwards to solve for my Ka value. So know that I can work in this direction to solve for percent dissociation given a Ka value, or I could work backwards by being given a percent dissociation and trying to find a Ka value. So this is some stuff they like to throw into the free response as well, calculating percent dissociation. So I hope this is helpful. We're going to do some example problems and practice problems in class, and hopefully you'll be able to do pH of weak acids and weak bases like a pro. So I'll see you later. Have a good night.